Yeah, in the end of the chapter, chapter 10, there are some accidental identifications. I didn't do that. Some of the things you already know, that, for example, SO3. SU2 is a double cover of SO3 that we have seen, right? That 2 points of SU2 are mapped to the same point in SO3. And then, yes?
Yeah, I have a question about basis of the metric tensor.
Basis of the?
Metric tensor. Previous lectures we just consider integer basis of the metric tensor. What is the difference if bases are fraction?
Basis for what? Basis for what is it? I couldn't hear very clearly.
Fractional?
No, basis for?
Not integer.
Sorry, basis for what?
Not integer, it is fraction.
No, but basis for what? Basis for the Lie algebra elements? Basis for what basis we chose? For the Lie algebra elements?
Yeah.
Yeah, I mean, you can, in a vector space, you can choose any basis you wish. There is no particular reason for that, for any particular choice. Huh? Just like, I mean, in the state, imagine two-dimensional flat two-dimensional plane. You could have chosen any basis, no? And any vector can be expressed in terms of any choice of basis. For example, so suppose I have two-dimensional vector space. Normally we choose orthogonal basis. No? Orthogonal basis, we say, okay, this is the x direction, that's the y direction, and I choose a basis vector 0, 1. I mean, in these coordinates. So 0 is the coordinate of the x, and 1 is the coordinate for y, and for this one I choose 1, 0. No? And then any vector, let's say this any point x, y. So let's call this as E1 and that as E2. Then I can write xy as this point xy as E1, I mean x times E1 plus y times E2. No? You can write like that. But that is just a particular choice. And I could have chosen, for example, a basis vector, something here and something here with any length, whatever I wish. No? But whatever it is, I can always express this vector as some number times this vector plus some number times this vector. So that's, maybe I didn't understand the question. So I could choose, for example, fraction. I mean, instead of choosing this, I could have chosen half 0. No? And 0, this could be,
yes.
Yeah, this could be 1/3. In that case, what will happen? Here it will become 2x, because if I want to express xy, so 2x times E1 and 3y times E2. No?
So, okay, I got it.
Yeah, all the statements that, in fact, particularly now that we'll be discussing the more formal aspects, all the statements we'll be making will be basis independent. Okay. So far we were using a lot of basis because we were working with explicit examples. And if you don't want to get some horrible numbers in various expansions, you better choose some convenient basis. That's the only reason, for convenience. There is no fundamental reason for any particular choice. So what I wanted to say was there are some sorry, going back to yesterday, just to finish that chapter 10. So there are some identifications. First of all, let's look at the SP1. Okay. We already saw SP1R. That this was nothing else but SL2R. Right? Remember that we looked at this arbitrary matrix. This is 2 by 2 matrix. I mean, if this is n, then we are talking about 2n by 2n matrix. No? So for 1, it is 2 by 2 matrix, and we wrote the most general matrix like that. And then when we impose the condition, that equation which says that for the group. Let's look at the group level. It was M transpose E M transpose. So this is say M transpose E M was equal to E. No? Okay, we were calling G. Okay, let me write. Since that equation is G transpose G. G transpose EG was equal to E. This condition, actually, as we already argued, the number of conditions will be simply, because both are antisymmetric. Both sides are antisymmetric. There's only one condition for this case. Antisymmetric just from here. So you find the condition is, this equation implies AB minus BC equal to 1. But that just says the determinant of G is 1. Okay. But that was exactly the definition of SL2R. SL2R was an arbitrary 2 by 2 real matrix, right? The only condition is that the determinant is equal to 1. So we conclude that SP1R is the same as SL2R. But now, if you go back to the, you know, from this was we said is non-compact. This group is non-compact. Just like SL2R is non-compact because A, B, C, D can grow as much as you wish. There is no limit on the values of A, B, C, D, right? Only condition is this. But you can take A to be very, very large. Simultaneously, you can take, for example, B to be very large, no? Keeping D and C fixed, no? And this condition can be satisfied. So that's non-compact. But then there was a compact version. Compact version of it was obtained by taking the, first of all, complexifying. So the first step here is to complexify. In other words, we are talking about SP1C. Which means again is a A, B, C, D, but now A, B, C, D are complex numbers. Okay. So now it's the same matrix, A, B, C, D, but now A, B, C, D are complex numbers. Okay. And this determinant condition, with this condition is still coming from there. This condition is coming from here, right? So this is still, it has to be satisfied. So AB minus BC equal to 1. But now they're all complex numbers, right? Now the procedure was to take the intersection of this SP1Z, SP1C. So now the idea is to take the intersection of SP1C with U2 group. But what will that do? I mean, U2 is a 2 by 2 matrix which is unitary, right? So entries are complex to begin with, but then you have unitarity condition. Now here we have an arbitrary complex, and the determinant of U can be anything, right? To begin with. So here we are taking the arbitrary complex numbers here. So when I talk about intersection, it means only those G's will be allowed in this intersection. So here is G. So this implies that this means that only those G's are allowed, those G's with the determinant equal to G, determinant G equal to 1 will be allowed, which are also unitary. So that would mean, that would impose conditions, I forgot not exactly, I think it was the condition was, well, I mean, okay, we can obtain the conditions from, just take the G dagger G equal to 1. So that will give me some conditions on A, B, C, D. But whenever those conditions are satisfied, that will be an element of U2, right? But in fact, more than that, because we also have the condition determinant of G equal to 1, so the intersection part will only be SU2, right? You see? So this is in fact SU2. So what we are saying is that I mean, in this lecture notes we don't use this notation, but usually people write it as USP1. So So this is the unitary version of a symplectic, which is nothing else but that, this guy. So we find that the compact version of the SP1, this is what is called the compact version. It's compact because whatever it is, it has to be an element of U2 also, right? So U2 unitary groups are compact. So in the intersection, every element will be, they will all span a compact. They'll be, it's a compact group. So USP1 happens to be the same as SU2. But that's completely a coincidence. I mean, the moment you go to a higher one, USP2, etc., then there is not. Well, it turns out the USP2 also, there is in the next page, I think. Yeah, USP2 is actually related to SO5. More precisely, it's a double cover. This is a double cover of SO5. USP2 is a double cover of SO5. Just like SU2 was a double cover of SO3. Double cover. It's a 2-to-1 map. 2-to-1 map. 2 points of here were mapped to the same point here. Same way, 2 points of this group is mapped to the same point of SO5. So, well, in this case, you see, we already said that SPn, the dimension of SPn was n times 2, I mean 2n times 2n plus 1 divided by 2, right? I mean 2 cancels, so it was just n times n, 2n plus 1. But the dimension of SO, 2n plus 1, is what? It is this times this minus 1 divided by 2, right? In general, SON, let's call it SON, dimension is n times n minus 1 over 2. No? This is general, SON. But now specialize the case where SO, n is 2n plus 1. Well, that is the same as 2n plus 1 times 2n plus 1 times 2n divided by 2, which is the same as that. So, for all n, dimension of SPn is the same as dimension of SO 2n plus 1. Okay? So, one might naively imagine that probably at the level of, I mean, maybe this is again some double cover or some cover of SO 2n plus 1. But that is not the case. The only special case is n equal to 2. For n equal to 2, these two are related by a double cover. In particular, when you say double cover, etc., it means the Lie algebra are the same. Because Lie algebra doesn't talk about, I mean, Lie algebra probes only the neighborhood of identity. No? So at the level of Lie algebra, as we saw, SU2 and SO3 were the same. There was no difference at the level of Lie algebra. Right? At the global picture, when you go to the global description of the group, then there was a difference between the two. Same thing happens here. The level of Lie algebra is the same. But for the other n's, even at the level of Lie algebra, they are not the same. Even though dimensions agree. They are completely different Lie algebras. So this is just coincidence. There's some coincidental identifications. But generically, this doesn't happen. I mean, we will study all this in more detail later. I mean, as we go along. Okay, I think. And similarly, SU4, if there are other things are given, SU4. SU4, the dimension of that is 4 square minus 1, so 15. And if you take SO6, its dimension is also 15 because it is 6 times pi by 2, which is again 15. The dimensions are the same. But in this case, the Lie algebra is the same. SU4 and SO6, the Lie algebras are the same. But again, it's at the global level, it's not the same. So again, SU4 is a double cover of. So this is again a map 2-to-1 map. But at the level of Lie algebra, it's the same. And finally, there is another group which actually plays a lot of important role in physics. The identification, this identification, SU2 times the direct product SU2 is the same as, is again a double cover. SO4. Is a This is very useful. I mean, in many of the physics calculations, this identification we use many times. The reason is SO4. I mean, in the 4 dimension. So in 3 dimension, you know the rotational group is SO3, right? If you go to the 4 dimension, which is the space-time Lorentz group, no, it's a Lorentz group, but it will turn out that many times to do the calculations, some of the calculations that we need to do, at the intermediate step, you take the time to be imaginary. Okay, it turns out. I mean, this you have not. You will study it again in the next semester. This particular thing. That if you look at I mean the 3-dimensional x and t. In that case, the length square is given by t square or dt square. I mean, if you look at the small difference, dt square minus dx square, dx1 square plus dx2 square plus dx3 square. Okay, there is a c here, but I can choose a unit where c is 1. No? There is c square here generally, but you can choose a unit, your appropriate unit that c is equal to 1. I mean, it's not important. You can keep c there, it doesn't matter. But in any case, so I put that. Now, what you do is you take, in the calculations many times, what happens is that in the intermediate step, as a kind of, to simplify the problem, what happens is that in the intermediate step, you take t, go to I times t. So this is real, but that's pure imaginary. So you do a continuation in the complex plane. You go to the IT. So then the metric becomes simply, you can take out the minus, that's not important, dt square plus dxi square. Some go around. Now you see here, you have an SO4 symmetry, right? Because SO4 precisely preserves this metric, 4-dimensional Euclidean metric. So there's an SO4 symmetry. So at the intermediate step, you see SO4. And many times in the calculation, it becomes easier to think in terms of SU2 cross SU2. There are actually, yeah. And then after doing all the calculation, you go back. You again go back to the real time. But this is a trick that is widely used. I mean, in fact, in many cases, we don't know how to do anything without going through this trick. You know? Because, I mean, things, expressions, various equations do not make much sense unless you go to in the intermediate stage. Okay, so, but you'll see that. I mean, so, and actually what I would like to do is, if I get the last lecture, I would like to look at all the SO and the spinor representations of all the SO spinor representations. I don't know if Eddie has done that or if Eddie is thinking of doing it in the RQL course. He has arrived at the Lorentz symmetry, right? Lorentz group. Yes. Right? Lorentz group. And okay, I don't know whether he is going to talk about spinors also. He must have talked about.
We take right? The spinor representation for the wave function.
Yeah, for SO3,1, for SO1,3, right? Yeah. So he did that, right? I don't know whether he's going to do general for any arbitrary SON, but it is again useful because many times you'll see in physics, okay, not so much in the course, but a lot of work which is being done research-wise is really sometimes you go above 4 dimension, no? And you think of our space-time as embedded inside some bigger dimensional space. So that the remaining extra dimensions, outside so suppose you start from 10 dimension. So you have the 4-dimensional Minkowski space in there, and then there is an internal extra 6 directions. Those 6 directions, you can imagine that they are very small size. They are kind of compact, let's say for example a sphere or much more complicated spaces, but their size is so small that they are not visible in the experiments. They are too tiny. In fact, in many of these theories which have been studied a lot in the literature during the last 40 years or so, is one theory is called string theory. Okay. So string theory is an attempt to unify gravity with quantum mechanics. No? And it seems it does, at least in perturbation theory, it does that. Huh? But if you do string theory, then it turns out that you have to go to 10 dimension. String theory is defined in 10 dimension. Okay. So then this question arises naturally. You compactify the remaining 6 dimension into some small space, and then the 4 dimension. But anyway, the point that I was trying to make is that many times you want to go to higher dimensions. And then you are interested in, so in higher dimension, suppose I work with the Euclidean metric, then this will be some arbitrary SOM. For example, in 10 dimension it will be SO10, right? Or if n for n equal to 10, you will have SO10 in the Euclidean signature. Euclidean, which means doing the Wick. This is called this. By the way, this procedure is called Wick rotation. This procedure to take t to it is called the Wick rotation. So if you do the Wick rotation, otherwise you have SO1, 9. Right? So in either case, you would like to understand what are the fermions, what kind of fermions, what are the spinors on this, for this. So for this reason, I wanted to spend one lecture on getting all the spinor representations for all the n's in a systematic way. But let's see, we'll do that if there is time. So for example, for SO4, if you want to talk about spinor representation, you really need to go to the double cover. Just like for SU, in SO3, the same representation is like SU2, except that the spins are integers for SO3, right? But if you want to talk about half integer spins, then you need to go to SU2. So this is also crucial here. Okay. So now let me go to the more formal approach. So this chapter 9, that is just one-page chapter. Yeah, chapter 9 is just one-page chapter. So, so far we are talking using the matrix groups. So in matrix groups, and we use just a standard matrix multiplication as the group composition rule. But now we'll just work with arbitrary. We don't specify anything is matrix or anything like that. So what is the definition of a Lie algebra? Because we really have not defined Lie algebra in a precise way. So it's a vector space. First of all, it's a vector space. And we are here denoting it as some V. So V is a vector space. And then, so vector space, of course, you know what it means. Any linear combinations of any of these elements is again an element. That's a vector space. And then, the most important new extra feature here is that there is a commutation relation. There is something which we call commutation relation. So this bracket is again inside Z for all xy. For all xy belonging to V. This symbol, whatever we are defining it also belongs to V. But the most important thing about that is it is antisymmetric. So in other words, xy is the same as minus yx. That is there. Then the Jacobi identity. So that's Jacobi identity. Okay. I mean, Jacobi identity is a triviality, is automatic if these are matrices, right? But now we don't want to think in terms of matrices. There's just some. Right? So therefore, since I'm not thinking in terms of matrices, I should impose this condition. You know? So that condition is simply what we already wrote, like x, y, z plus y, z, x plus z, x, y equal to 0. So that's Jacobi. So this bracket must satisfy this condition. And this bracket also preserves a vector space structure, which means if I take ax plus dy commuted with some, say, z. That's the same as A and B are numbers. X, Z, plus B. That's it. So this just means that, I mean, V has a vector space structure. So whatever bracket you define better also satisfy that vector space structure. Should be consistent with that vector space structure. So these are just the 4 definitions. Okay. For the matrices, all these are automatic. If these are matrices and this commutation relation was simply the matrix commutation relation, meaning if this was if X and if the V was all a space of matrices, then all these are automatic. Then some matrices, some square matrices, n cross n matrices. Then you see and define this commutator. In that case, you just define the commutator as simply xy minus yx, where these are simply matrix multiplications, right? Then you see that all these properties are automatically satisfied. All the other conditions are satisfied automatically. But since we don't want to think in terms of matrices, we just formalize these rules. Okay. Then, so this is the Lie algebra. Then, what is a subalgebra? So, subalgebra of, say, V, so let's say some W, let me use the same notation. The W, in fact, also notation is W. So, there is subalgebra which is containing V, the original algebra. Okay. And then what we are saying is that if X and Y belong to W, for all XY belonging to W, X commute with Y with whatever the rule you have defined, no? Here. With that rule, this commutator is also contained in W. Okay, if this is contained in W, then because of this here, obviously these are also contained in V, right? And then we just use a commutation relation which we defined in the V and see what it is. This is certainly contained in V, of course, from those definitions. But what we are demanding is more. We are saying it should be actually contained in this subset, in the subspace. Okay. If that happens, then you say W is a subalgebra. W is a subalgebra. Oh. Okay. So this is all of this is very much also in the group, right? Remember when we talked about the group and we have a subgroup, what it was that we have to make sure that if I take 2 elements of the subgroup, or what we call subgroup, right? When you use a composition rule, but composition rule defining the original group, not some other new composition rule. The one which is defined in the original. That is what it means to say that at the level of Lie algebra, that means we use the same rules that we have developed for the B. We have to use this same rule, not some other rule, right, to define this. In that case, you call it. So same way for the group, right? We have to use the same composition rule of the original rule. And with respect to that, if the product of 2 elements is again the subgroup is again, I mean subset is again contained in that subset, then you say it's a subgroup, right? So it's the same thing here. Okay. And of course, subgroup should have identity, etc., etc. So this is the subalgebra. But now there is some special, this is important. Oh, I don't have that sheet here. But anyway, there is one more thing. There are some special types of subalgebras. Okay, this is subalgebra, right? But there are some special subalgebras which are called invariant subalgebras. And this plays an important role in the classification of all the Lie algebras. So that's why I'm mentioning this. Okay. There is a special class of subalgebras which are called invariant subalgebra. Okay. Or many times in literature is also called ideal. It's the same thing. In some literature you will find they use the word ideal. In some literature you will find invariant subalgebra. They are the same. So what it means is that so let's say invariant subalgebra W. W of V. Okay. So first of all, W must be a subalgebra. That is, must be a subalgebra of V. But there is further condition. The condition is that if X belongs to W, for all X belonging to W, and all Y belonging to V, the commutator of XY is in W. So you see, this is a much stronger condition. Because here we are saying that only has to be true only both X and Y are in W. But now we are saying that if one of them is in X, one of them is in W, and the other one is in any element of Y, the original algebra V, the commutator is still inside W. Okay? So this is a much stronger condition. So if that happens, then you say that W is called, and W is called invariant subalgebra or ideal. Ideal of V. Just to give some examples.
Professor, I have a question.
Yeah.
So does this W, the algebra W, is this a vector subspace?
W is what?
Is a vector subspace. I mean, if we take the linear combination of X and Y, will it also be?
Yeah. So W is a sub-vector space. I mean, so first of all, already I should have mentioned that. It's a sub-vector space. So these are all vector spaces of right? So indeed, yeah, you're absolutely, that's correct. So this of course means that if for all x, y belonging to W, any number ax plus by is also in W. Yeah. So yeah, to begin with, we are already saying that W is first of all a subspace of V. So vector subspace, sub-vector space. So yeah, that is automatic. Yeah, that is inherent. So it should be, really I should have added that also. Yeah. Okay. So to just give some examples, let's say, for example, let's take, I can erase this part, right? So for example, if you take SU2, let's just take SU2. SU2. And so this is generated by sigma 1, sigma 2, and sigma 3. Right? So in other words, arbitrary element can be expressed as a linear combination of Pauli matrices. Then consider the U1 subalgebra. I will call U1 subalgebra. U1 subspace, let's say. Which is just generated by sigma 3. This is perfectly okay here because I mean sigma 3, so sigma 3 commutes with itself is 0, so 0 is also an element of this U1, right? Because any number, so we are saying any number times sigma 3 is an element. That's a one-dimensional vector space. This is three-dimensional vector space, which means any element A sigma 1 plus B sigma 2 plus C sigma 3 is an element of this U2. SU2 Lie algebra. So we take this one-dimensional subspace, which is generated by sigma 3, and then sigma 3 commuted with sigma 3 itself is 0. So this, of course, is an abelian algebra. Right? So it's a clearly subalgebra. It satisfies the condition of subalgebra, the fact that it is subalgebra of SU2. So we have a U1, which is a subalgebra of SU2. But what is it? The question is it one of is it an invariant subalgebra? That's one question you can ask. So we want to ask that is it invariant subalgebra? And the answer is no, because if I take sigma 1 with sigma 3, the commutator, this is not in the subalgebra here. This is actually sigma 2. I mean 2i sigma 2 or minus sigma 2, something like that. But whatever it is, it's not in sigma 3. No? So this U1 is not an invariant subalgebra of SU2. It is a subalgebra, but not an invariant subalgebra.
Can we consider the raising and the lowering operators something like this?
Sorry, repeat
Can
again.
we consider the raising and the lowering operators as the sum?
Sigma plus, well, not really again, right? Because, I mean, if I take sigma plus with sigma minus, it gives you sigma 3, right? Some number times sigma 3. Not really. So it's not, I mean, so none of them. But on the other hand, if you take U2 is generated as 4-dimensional. U2's algebra is 4-dimensional. So it has identity and sigma 1, sigma 2, and sigma 3. So it's a 4-dimensional. Yeah? So any linear combinations of this is part of U2 algebra. And now there is a subalgebra which is just generated by U1. So you consider the U1 subalgebra which is generated by the identity matrix. This is clearly subalgebra because the commutator of 1 with 1 is 0. No? The subalgebra. But it's also invariant subalgebra because one commutes with any of these combinations, right? Any combination, you take whatever A times 1 plus B times sigma 1 plus C times sigma 2 plus D times sigma 3. This is 0. So in particular, it is a 0 times 1. No? I can write 0 times 1. So that's an element. So it's an element of this U1. So here we have an invariant subalgebra. For U2, there is an invariant subalgebra of this U1. Slightly more complicated example one can consider. You have looked at you have seen the Poincare algebra, right? In that course, in the RQM course, or not? Poincare, Lorentz algebra you have seen. Poincare algebra, you have not seen. It's basically okay. Let me not even do the Lorentz. Let me just do a three-dimensional Euclidean space. Okay, which has the rotation, the 3 rotation generators, and also the translation. Euclidean geometry is also translational symmetry, right? It has 2 symmetries: rotational symmetry and the translational symmetry. When you combine these 2 transformations together, that is what is called Euclidean algebra. Same thing happens for in the 4-dimensional space-time, 3 space and 1 time. The rotations between the space and time is what is the Lorentz transformation, because rotation has to preserve that metric, minus, plus sign. No? So therefore that's not the standard rotation, but it's a rotation in that metric. So that is the Lorentz part. But you also have the translational symmetry. You can translate the space, you can translate the time. No, you can do that. But when you combine these 2 symmetry transformations, then you get what the group which is called Poincare. So Poincare group has, there are 6 Lorentz generators, and 4 translations because we are talking about 4 space-time. So Poincare group is a 10-dimensional. And therefore algebra is also 10-dimensional algebra. Same thing happens with the Euclidean 3-dimensional. What will happen? The rotation part is 3-dimensional. That's nothing else but SO3. So this is 3-dimensional. And the translation is also 3-dimensional because I can translate in X direction, Y direction, or Z direction, 3 independent directions. So that's 3. And the group that is composed out of that is called the Euclidean, 3-dimensional Euclidean group. Okay. And basically the algebra of that is the following. Okay, I'll just write down this algebra. If you take, so the rotation, I will write the rotation generator, usually we write as Ji, no? So Ji means it is rotation with the axis along the ith direction, no? So if I say J3, it means the axis is 3rd direction, so rotation is happening in the 1, 2 plane, no? So instead of that, I will use I will put the index ij. So this means if a rotation is taking place in the ij plane. So the axis is perpendicular to ij plane. Okay. It's just more convenient, that's all. So if I look at this algebra Jij, JKL, this is going to be, I'm not sure about the numbers and so on, but it's going to be basically like JIL. There will be 4 terms. JIL delta JK plus, then you just antisymmetrize, because this is antisymmetric in IJ, this is antisymmetric in KL, so you just antisymmetrize. So there are 4 more terms, 2 minus signs and 1 plus sign. You understand? Just, for example, IJ is antisymmetric, so I should antisymmetrize. So one term would be JK delta IL, okay, minus, now it also antisymmetrize in KL, so I'm going to get JIK delta JL, and then finally there is a term which is, because I have to also again antisymmetrize this with the KL, so I'll get minus minus plus JL delta I. Right? This is I think this is a similar expression you had for Lorentz, right? Lorentz algebra, where you had, I think this was written L mu L lambda sigma, no? And then instead of delta, it will become eta, the Einstein the space-time metric. So instead of delta, it will be eta, because eta is a metric there in the Minkowski space. So it's a similar expression. But then you also have the translation. You need to also worry about the translation. First of all, the translation, if I take 2 translations, let me call the generator of translation as P, because P, momenta, are the generator of translations. Right? Remember that when we studied the conservation laws, Noether theorem, we saw that translations correspond to conservation of, translation invariance means momentum conservation. No? So momenta are the generators, actually. It's even clear in the quantum mechanics, because when you make x goes to x plus a, where a is infinitesimal, that's nothing else but taking the derivative d by dx. No? So if I take some function f of x, so when I make a small change, x plus epsilon, let's say epsilon, x plus epsilon, then I can ask the question, how is it different from the original? So minus f of x, right? So you have some function of x. I make a small translation in x. So you have this. And now you see what's the difference between these two. That will be the generator, right? But then you can make a Taylor expansion, and that's nothing else but f of x plus epsilon df by dx. Right? To first order in epsilon. And then plus higher order in epsilon squared. Minus f of x. So this cancels. And you find the generator is nothing else but d by dx. No? So d by dx is basically plays the role of the generator for the translation. You can think. And that is what you see in the quantum mechanics, right? Momenta are basically up to some factors of I and h bars and so on, is basically d by dx. No? So that's the d by dx. And so then you can write down the translation generator. So I will just call it momentum. Call the generator as momenta. So translation generator, there are 3 of them because we are working in 3 dimension. Okay. And so pi, I again goes from 1 to 3. They commute, of course. Pi, tj is 0, because whether you first translate it on the x direction, then translate it on the y direction, is the same as if you first do the translation on the y direction and then the x direction. So this commutes. But this do not commute. Jij, pj, jpk, let's say, this commutation, what it is going to do? This is a vector in 3D. And that just rotates. So this is going to rotate the p, the rotation. No? So this is going to be, again, I'm not sure about the overall signs, delta jk pi minus delta ik pj. Right? You see. So if I, for example, let's say, suppose this is 1, 2. 1, 2. So we are rotating around the 3rd axis. So 1, 2 plane I'm rotating. No? 1, 2 plane I'm rotating. So if this happened to be P3, then it will do nothing. No? But if it is in the first direction, it will rotate to the 2nd direction. No? So that's why if it is first direction, then this J12, so there is a delta ik, so that term, and it rotates, it gives you the P2. And similarly, if you take this along the 2 direction, if k was 2, then you get delta jk and P1. So this is the rotation. So this is the basic algebra of the. Again, I'm not sure about the overall signs and so on, but the general structure is, could be plus or minus, and here also I'm not sure about the signs, but okay. The signs depend on your precise definition of J and P. So that's not so important. Okay, so with this algebra, now you ask the question, what are the subalgebras? Okay, there are 2 subalgebras we can immediately see. One, so this is what is called Euclidean, the 3-dimensional Euclidean, 3D Euclidean algebra. Okay. Now we have 2 immediate subalgebras. One is just the rotation part. So one subalgebra is just a rotation part. So in other words, this is generated by J12, J23, and J31. I mean, this is antisymmetric, IJ. So there are 3 generators there. So this clearly, because if I look at the commutators of any of these, I'm getting back again one of the J's. That was the definition of the subalgebra, right? If I take in arbitrary elements of these, take the commutator, it stays within them, within as linear combinations of this, which is what we see here. This is all combinations of J's. P doesn't appear there. P doesn't appear there, right? So this is subalgebra. Let's call it V1 subalgebra. This whole thing is V. The J's and Jij and Pk, all of them together generate what we call, let's call it E, the E3. The E3 Lie algebra. So this is one. So this is nothing else but this SO3. SO3 subalgebra, generated 3-dimensional rotation. Then the second thing, the translation, the 3D translation of algebra, which is generated by P1, P2, and P3. This is also a subalgebra because P with P actually is 0. So it's just a abelian subalgebra. But now you ask the question, which are these invariant subalgebras or not? Now you see that if I take, so the question is it invariant? So let's look at SO3 first. First of all, let's look at SO3. So if it is invariant subalgebra, then we want to show that we should have a property that Jij with any x, where x belongs to E3. For all x belonging to E3. This must be again in the SO3. No? In the SO3. Which means the combinations of j's. This must be again some combination of Jij. But no, P should not appear there. Because P is not in this subalgebra. No? But notice this is not true. While if x is one of the j's, it is true. But if x is P, then this is not true because the right hand side is P, involves P. So this is not. So this is not a subalgebra. So it's not an ideal, not an ideal. On the other hand, if you take the second one, so which is the translation, so here is P1, P2, P3. So we are asking the question, if I take any Pi and an arbitrary x, is it again sum of the Pi's? And that is true because the P with P is of course 0, but P with J gives you back again P. No? Combinations of P. J doesn't enter here. Okay? So this is an ideal. So the translation part is an ideal or invariant subalgebra. So there are these things happen. This, by the way, this algebra, I mean, if you see, this is not, what do you call, when we talked about the direct products of the groups, so at the level of group, what this is telling you is that this group, this is a SO3 group, this generates SO3 group. When you, not just, this is infinitesimal elements, but now when you take the finite transformations, this will generate SO3 group. Similarly, translations will generate R cube, what we were calling R. R was a translation along one direction, right? This will be R cube because you have three directions. So you have R cube for the translation, okay, and SO3 for the rotation. Now, when you take the, if you take the direct product of these two, then of course there should be this commutation relation should not be there. I mean, they should commute, but if it was a direct product. So what this is called, this product is called, is what is called semi-direct product. There's a term, semi-direct product. So the semi-direct product is defined in general, is something like this. If I have some group G and let's say another group H, and I want to take the semi-direct product, I don't know how to write, and let me put here S to indicate that this is not, this is semi-direct product. Okay. I'm sure there's some symbol for it, it's direct symbol, but I'm just using this means semi-direct product. Semi-direct product. This can be defined provided there is a, I mean this is going a bit out of the main topic, but since I start talking about it, I mean suppose it happens that G acts on H as an automorphism. Okay? Suppose G acts on the H as an automorphism, or automorphism would mean, so that means for every G belonging to capital G, there is a map, G maps H to H, okay, which satisfies all the product rules of the H. In other words, if G is maps H to GH1, I call it GH1, H1. So let's say H1 is mapped to something which I call GH1, which is an element of H. But it depends on which element, depends on which G you're talking about, right? So that is the reason why I put here G. If H2 maps to GH2, then G of H1, H2, where this is a composition rule inside H, is the same as G of H1, G of H2. So this is what I mean by it preserves the group product rule of within H. So the statement is that suppose such an automorphism exists. Suppose such an automorphism. And this happens in this case because you see, if I take any, think of this group as the translation group in our example, and this group as a rotation group. Okay. So this is indeed true. I mean, you see, what is this map? Given any rotation here, I can define a map on this translation. You take whatever the translation will be some vector in the 3 dimension. You just rotate by that element. So that is automorphism we're talking about, right? So every vector will be rotated to a vector given by this rotation. Whichever rotation you're talking about, and it will satisfy this property. Okay. I mean, so in this case, in that case, this is a translation, this is a translation, so this translation, and this composition rule is nothing else but addition of 2 vectors. So you have, say, the vector v1, vector v2, translations, and this is addition, and G of H1 is simply the rotation of the v1, and v2 is also rotated. So you take the rotated H1, rotated v1 and rotated v2, add that up. That will be the same as the rotation of the v1 plus v2. No? You see what I'm saying? If I have a vector, and okay, it's difficult to draw in 3 dimensions, so okay, some rotation here. The sum of it is this, right? That is what this composition rule is. Composition rule is, so this is some H1 vector, H2, then the sum of that is that. No? Now, I rotate all of them, right? So if I rotate this and I rotate that in any direction, okay, suppose I rotate in this plane. So H1 gets rotated, it comes here by some amount. H2 will be rotated by the same angle, it will be there, okay? And then if you take now the sum of these two, it will be this vector. No? But this vector is exactly the same as the rotation of this by the same amount of angle. So it satisfies this condition. But in any case, I mean, this condition, when we say automorphism, this is what it will be. It should satisfy this condition.
Professor?
Yeah?
I have a quick question. So that you wrote G semi-direct product with H, the G and H are groups or Lie algebra?
Yeah, I mean, so perhaps, yeah, maybe I should. Really, here I'm talking about the Lie algebra, but let me go back to the group. But the group, it is that. Similarly, we can define the, I mean, let's call it G, small g, as a Lie algebra, and here, let's say, H, the corresponding Lie algebra. You can again talk about the direct sum. Here. It's not the direct, because the level of, I mean, even for the direct product, at the level of Lie algebra, it becomes direct sum. So here I'm talking about the group, but that is equivalent to saying that at the level of Lie algebra, there is a semi-direct sum. Yeah, right.
And also, I was just mentioning that if it happens that G times H times G inverse belongs to the Lie algebra H, then we can actually consider a kind of the mapping that you mentioned, which acts like, if we consider this mapping, it will happen that I mean, it will satisfy the property that you mentioned.
Yeah, exactly. If H is in the invariant subalgebra, and you look at the adjoint map of G, no, adjoint map of G, which is exactly what you're saying, G inverse HG, that again belongs to the. If it is ideal, then it should belong to the same subspace. Yeah, correct. Yeah, exactly. Right. So yeah. So if this happens, then you can define. Then you can define a semi-direct product in the following way. So if I have G, so let's say an element of this direct product will be some G belonging to capital G and some H belonging to capital H. Okay, this is a pair of elements. That is the direct product group. And so suppose now I take the product. So I have a G1 H1 and G2 H2. So we want to define a product rule, okay, in this semi-direct product. So how do you define it? You define it as G1, maybe I should, okay, G1, G2, but here is the product rule is that of G. The product rule is that of G. And H1, and here the product rule is that of H, right? But H1 with not H2, H1 with G1 automorphism acting on H2. So this is the difference. Whereas, I mean, if it was not semi-direct product, then there would be no such thing. It would be simply H1 times H2. So this is the difference between that. So you see, if it was a direct product, you would say if it is G times H, the direct product, then product rule will be G1 H1 times G2 H2 times G2 H2 is simply G1 G2 times comma H1 H2. Okay, where again the rules are here that of the G, here that of H. So that's the difference between these two, semi-direct product and direct product. So semi-direct product you can always define, provided this group acts as an automorphism on this group. And Lorentz group, or this group, Euclidean group is exactly that. Here is a rotation, translation, but the product is defined as this rotation times rotation, but here is this translation plus the translation which is obtained by applying this rotation, G1 H2. Okay, so I will, now let me just, this was a bit of a, what is the time? This one I think I unnecessarily took too much time. Okay, so let me now go to the next chapter.
Professor, I have a question.
Yeah.
So here we see that the rotation operators and the momentum operators, they produces a Lie sub-algebra.
Produces a
Lie sub-algebra.
Lie algebra.
Yeah. I
Yeah.
mean, the rotations, they themselves produces a sub-algebra, right?
Yes.
And also the momentum operators.
Yeah. This here, these two equations, right? Yeah.
Yes. So,
Yeah.
and we can see that if we look at it from a group picture, the rotation and the translation, they form a subgroups, right?
That's right.
So is it a general kind of thing? If we have two subalgebras, then their corresponding group will also form subgroups.
Sure. Yeah. This, I mean, we said that both of them were subalgebras. You exponentiate these subalgebras, then you get the group SO3 and the rotation. So it's really at the level of, in this example, it's SO3 semi-direct product R3 in the example. R3 being the translation. R cube being the translation. Yeah, correct. But it's because of this twist. I mean, this twisted, I mean, kind of slightly modified product rule. That is what is, that's the reason for this. And I mean, this is actually in some sense, I mean, this is what you will do physics-wise, no? Because, let's see, where's the chalk? Yeah. Because if I think of, let's say I start with some point in some three-dimensional space. I cannot draw three-dimensional space. So there are two elements. One, so let's say I define, what do I mean by GH? The GH. So this means some rotation, and some, okay, and some translation A. Okay, so I take a vector, arbitrary vector here. What do? I have to define it in some way, how it acts. Well, it rotates. I can define it in this way or the other way, which I will explain to you now. So I rotate by, say, some angle theta, some r theta, let's say, rotate. So I come here, and then I shift by A. A is some particular vector. Say A is this vector. No? So I start with some vector V. First I rotate, R, so this I call RV. And here, then I have to add also, the shift also. So it's R, V plus R. This is the new vector. Now, suppose I apply again another operation. So let's say R prime, theta, and A prime. On this. So first I apply this, then I apply that. On the result that you get. Okay. So what I will do? So this I will now start from here because I am looking at, first I apply this on the vector V. I get, what do I get? So maybe I should draw it. So first I apply this. So I get here R theta V plus A. Right? This is what I get. So this V goes to that. Now I apply the second one. So this was just the first step. This was the action of it. Right? Now on this result, I need to apply the second element. So here I am applying now R theta prime, A prime. Well, the result will be, I rotate this whole thing by R theta prime. So it's R theta prime, R theta V plus R theta prime acting on A. Okay, this is just a rotation acting on this. And now I add this A prime. So you see in the composition rule now, what has happened? You see the composition rule now is that you get here R theta prime, R theta, that is the first element, because that's just the rotation of the original vector V. And then the translation has become R theta prime, A plus A prime. It is not just A plus A prime, it is R theta prime acting on A plus A prime. But what is this? This is nothing else but automorphism of A, the rotation of A, which is what I call here, this G1H2. So just from the way we define the Euclidean group, the product rule is actually the semi-direct product rule. Yes.
to consider the algebra as a tangent space at the identity. And now, in today's lecture, we started the concept of algebra from in a much more formal way. We defined some properties, and we didn't actually require that the algebra elements must be matrix. We considered some general elements,
Yes.
which might not be matrix in general.
Yeah.
So, I mean, is it always, does it always happen that if we take the exponential of a real algebra element, it will automatically satisfy the properties of a Lie group?
Yeah. I mean, so exponential. No, actually, yeah, true, of course, yeah. But actually, one way to obtain all this Jacobi identity is already from the group composition rule. You know, this we didn't go through it, but if you start from the group has some properties, right? That it should be closure, associativity, etc. No. So now, if you take those properties and now write the G, arbitrary element as exponential or small, 1 plus epsilon, something, and then you will find with sufficient number of manipulations, you have to do some manipulations, that all of these conditions that we wrote down for the Lie algebra, it just follows from that. So you don't need to use any matrix realization of this. You can directly obtain that. Yeah.
And the relation is 1-to-1, right?
Yeah.
We go from both ways.
Yeah. That's true. Yeah. Actually, the commutator, what the commutator measures. So if I look at the xy, so I could, so let's say if I take G to be some e to the power of epsilon x, e to the power of epsilon x, and you ask the question, and I look at the add G action on y. Well, there's nothing else but G inverse yg, or G by G inverse, whatever, you can define it either way, G inverse by G. And now substitute this here. So you see, this is nothing else but just expand it. So let's write it as 1 plus epsilon x. No? So you get here, so this is 1 minus x. Maybe I should write it other way. Okay, let me put here G inverse, doesn't matter. So you get here 1 plus epsilon x, and there you get 1 minus epsilon x. And you see that the result is simply y plus the epsilon times the commutator of xy. So the commutator actually measures how in this, so it's like, so geometrically what is happening? The group manifold is something, no? Some. Maybe the identity is sitting somewhere here. And you look at x, which is some element which is near it. So it's like you take 1 plus x, no? 1 plus epsilon x. So I'm looking at some point nearby in the tangent space. Now what do? I first go from here to G inverse, this one. Then I look at again this tangent vector there and come back by G. So you first go from identity to G inverse, then you go to this tangent direction there, and then return again. When you do that, you will not get back the original vector in general. So in general, if it is not abelian, if it's abelian, of course you will get the original vector. But in general, it will not. And this commutator exactly measures that. And so similarly, then you can do further. I mean, you can apply one more G and start looking at the associativity relation. Okay, and from that you can deduce the Jacobi identity here. So yeah, this is true. I didn't go through it because it's a bit of a mess, but okay, you can try to do that. Okay, now, so now the thing goes to the half an hour left. Oh, not even half an hour. So let's see. Okay, now so one of the very, very important concepts which we are going to talk about. I think somebody also already raised some point here about the metric on the Lie algebras. No? Because so far we have not defined any metric on the Lie algebra. Lie algebra is a vector space, right? Which has the commutation relation defined. No? That's it. The commutation relation has to satisfy the Jacobi identity, etc. and vector space structure. But apart from that, we have not introduced any concept of metric. So this is where the metric, so we are now going to introduce a metric. Okay? So this is called the Cartan-Killing form. Cartan-Killing form. Okay. So this is defined in the following way. So the definition is, if I take X, suppose that I have some Lie algebra V, form on Lie algebra V. So it's defined as, so this is, I don't know why it's symbol B, but okay, in this lecture notes we'll be always using the B for the Cartan-Killing form. So given for all X and Y, belonging to B, Bxy, this Cartan-Killing form, is defined as a definition, is defined as a trace of add Y, add X. Okay. Right. So what do I mean by trace? I mean, so far we're saying we're not even talking about the matrices, no? So what do I mean by trace? The Y, sorry, XY. Is this because the add is defined just by using the commutation relation, right? After all, add Y acting on some Z is nothing else, that was our definition, YZ. And this we know precisely. I mean, this is already in the definition of the Lie algebra. Right? We never use any matrix or anything like that. No? This is a definition, it's already defined. It comes with the definition of the algebra. So this is known. So therefore, I can always think of add Y as suppose the dimension of the vector space V is say n, then I can think of add Y as an n cross n matrix. N cross n matrix. Right? Because I can just choose any, I mean, I'm not going to go through that. In the notes, I mean, you have one can rewrite it as, if I choose some basis Pi, basis for V, then I can always write Z as some Zi Pi, right? Some combination say Zi Pi, some number. These are some numbers, I going from 1 to n. So then I can think of this Z in this basis as just a column vector, Z1, Z2, up to Zn. No? And then similarly, on the right-hand side, you'll get something, but that something, again, I can write it, expand it in the same basis, right? So it's going to be, and it's going to be linear in the Z's, these coefficients Zi's. So I can always write it as some matrix. That matrix depends on the Y, so this will depend on Y, but it will be n cross n matrix acting on Z1 up to, so Z1 goes to Z. No? So the right hand side, which is a commutator, so that means add Y acting on this guy is equal to some n by n matrix which will depend on the Y. Is that clear to you? I mean, because this is linear in Z, no? I mean, this preserves the vector space structure. The commutator preserves the vector space structure. So if I rewrite this as Zi Ti, okay, then what is this commutator? This commutator is nothing else but Zi, commutator of Y Ti, sum over I. Right? Y Ti is something, some number, let's say, so not some number, some object. But I mean, it's again going to be whatever it is. I can expand it again in terms of it is going to be in element of the Lie algebra. So I can rewrite again as some numbers. Let's say yk, tk. No. The yik tk, because it depends on which I you take. Yik tk. So then this combination simply becomes sum over Zi, yki, tk. Zi, okay, I put also the index for that. So this is what you get. So in other words, this if I call, so this is nothing else but zk prime, right? because I'm expanding everything in the basis, so this is zk prime. So zk prime is simply given by this matrix yki, which is an n cross n matrix, multiplying the zi. So the statement is that add y is basically an n by n matrix. Okay? If you choose a basis, you can explicitly write down these matrices, n by n matrices. But in any case, it's n by n matrix. So, and similarly, add x will be another n by n matrix, because here these coefficients, if I take the commutation with the x, it will be some other coefficients, xki. Okay? So it will be again another matrix n by n. So these are both n cross n matrices. Then I can take the product. Product is again n cross n matrix, and the trace is well defined. You know what you mean by trace. Huh? So it's in that sense. This is the meaning of that right hand side. Okay? So each of them is a matrix, a square matrix. Each of them, the dimensionality of the n being the dimension of the vector space, and then you take the trace over it. Okay? So this is the definition. And so of course, this by construction, it is symmetric in x and y. Because in the trace, I mean, if I exchange y with x, in the trace you can move the matrices. No? So this is symmetric. So b xy is the same as b y. So it is symmetric. So this is okay, so one may ask the question, okay, I mean, I could have chosen any metric. Why this metric? Why this particular metric? The reason is that this metric has some interesting, important properties. I mean, you want your metric to have some, let's say, some important properties. One property that you would like to have is that suppose that there is an automorphism of some kind of an automorphism. Okay, one question you can ask is the following. So suppose I have some automorphism which takes the V to be some automorphism phi, let's say. Okay. Use the same symbol here. So there's some automorphism phi. In particular, I could have chosen this phi to be simply the adjoint, add action. Okay. Add action is an automorphism. But let's just take a general phi, completely arbitrary phi. So what does it mean by automorphism? So automorphism means that, of course, phi acting on B takes to B, that was already. But it also preserves the vector space structure. Vector space structure. And space structure. And the commutator structure, commutation relation. Okay. So vector space structure is simply this. I mean, if I apply phi on ax plus by for arbitrary two elements, x and y belonging to B, then that's the same as a phi of x plus b phi of y. Okay? So that will preserve the vector space structure. And the commutator structure is a statement that phi, if I look at the phi of x commuted with phi of y, and take the commutator of these two, then that's the same as a phi of the commutator xy. These are the two important points. So you see the meaning is that if I take xy commutator is something which is a commutator xy. So again, draw the picture. So here is in the size some vector space. V is a vector space. Say x is this point, y is this point, and say the commutator of xy is this point. Okay? In the vector space. Now what we are saying here is that if I take the phi of x, which will be some point, I mean I'm just drawing it separately, it could be the same for some, you don't know, I mean it could be any point. So I just call it phi of x here, and this point is say phi of y. And if I take the commutator of this, so the commutator of phi of x, phi of y, will be some point. No? Okay. Now what we are saying is that this point is not just arbitrary point. It is the phi acting on this. So you see this is mapped to that point by phi. Sorry, this point. Phi. This is mapped by phi. So this is taking, phi is taking to that. Then we are saying if I take the commutator of these two elements using our Lie algebra rules of the commutational relation, which has been defined in the Lie algebra. I just take this commutator, I will get some point here. But this point is not just some arbitrary point. It is the one which you would obtain by applying phi on this. That is the meaning of this relation. So if you do this, then, so let us see what would be the, we are asking the question, so what we are asking is that if this, what we'll try to prove is that this metric or this Cartman-Killing form that we have defined is invariant under the automorphism. Okay? It means that what we want to prove is that b of px, b of comma phi of py is the same as b of xy. Okay? This we want to prove. So this is important property that this definition satisfies. If I had not used some other definition for the metric, then that will not in general satisfy this condition. This is the important condition. So to prove this, so let's see how. So we just have to apply this definition. So we want to look at what is what is the add of phi and add of px. That's what we want to look at. So let's look at what is add of px acting on an arbitrary element z. Because add is basically this is defined by how it acts on an arbitrary element z. Well, that's nothing else by definition phi of x, the commutator of phi of x with z. That was the definition of the add action. But this I can rewrite as phi of x. So I should also mention that automorphism is a one-to-one map. This means that the inverse exists. So what this implies is that phi inverse exists. Right? Because if I have some space, and it is mapped, is a one-to-one map. Every point is mapped there, it's somewhere, and is one-to-one. So this is a map, phi. Phi inverse is the map other way. No? Phi inverse just takes this point back. If suppose it was a 2-to-1 map, if this was going, both of them are mapped there, then it's ill-defined where the phi inverse should take you. No? So if it is a 1-to-1 map, then a phi inverse exists. Because there's a well-defined, and if x goes to y, then y goes to x under phi inverse. It is completely well-defined. So phi inverse exists. So therefore I can write this as phi inverse acting on z. Okay. So first I apply phi inverse on z, and then again I apply phi on that, I will get back to z. No? It's just a way of writing. Okay. But this combination is nothing else but the phi of the commutator by using this property, is the commutator of x with phi inverse z. Okay. Which is the same as phi of add x. This is the definition of add x acting on phi inverse z. So this then tells me what we are doing there. So this whole thing, so therefore the conclusion from this is that add phi x is nothing else but it is phi add x phi inverse. So you see, first you apply phi inverse on the z, then you apply add x on that, and then you apply phi on that. okay, on an arbitrary Z. So that means add of phi x is the same as phi add x phi inverse. That is there. Now, similarly, add phi y, add phi y, add phi y will be phi add y phi inverse. Okay. Now so this by definition, so left hand side by definition is, this by the definition of that is the same as trace add phi of x add phi of y. Okay, but then I substitute add of phi x as that and add of phi y as that, and then so what this became, this becomes trace, and then you get here phi add x phi inverse and phi add y phi inverse. That's the trace. Phi inverse phi cancels out, gives you 1, and in a trace you can do cyclic rotation. So this phi inverse t cancels out, and you're left with add x, add y, which was b of xy. So that's a very important property. It means that if I define this, so again pictorially, what it means is that so pictorially it means I have this picture here. I have say x and y, two elements, and this definition b of xy gives me a bilinear form, it's a symmetric bilinear form, right? Symmetric because bxy was equal to byx, and this is what you would, I mean, if you, so this can define to you a metric, right? I mean, if given any two vectors, what you are giving is an inner product between these two vectors, right? So this gives you like a dot product, some kind of a dot product, some inner product. So we are giving some inner product between these two. Yeah, okay, it's some number. So this inner product, so b of xy, gives me the inner product. Let's say I just use this word. Because indeed, actually this is b is a metric actually, so it gives you the inner product. Between x and y. X and y. Now, phi is an automorphism. So phi takes you to some point phi of x, and phi takes y to some point phi of y. Okay. Now, what this equation is telling is that the inner product between these two is the same as the inner product between these two. Okay. That is the point. This is a very important property, and that is the reason why we use this. We want this kind of a property for the whatever metric we define. It should satisfy some property like that. Because in particular, add G. I mean at the group level, add G is an example of an automorphism. Okay. But here I'm talking about a completely general automorphism, which may not be add G only. There could be more than that. But add G itself is an automorphism. Okay. So we are saying that under the add G, if add G takes you from here to there and there to there, then the inner product between these two is the same as inner product. So it's like a G invariant, group invariant. No? So in that sense, this is group invariant inner product. I mean, so this is a natural inner product. No? If you had used some other metric in the vector space, it will not have some nice properties. It will not be group invariant in particular. No? Here, this will be group invariant. So that's the Cartan-Killing form. And okay, in the notes,
Professor, is this mapping in the same vector space, or it can be in other vector space?
No, phi is automorphism. Automorphism means back to the old. Yeah. So it's a automorphism of B to B. Yeah, I mean, in general, of course, automorphism also exists. Maps exist. Isomorphism, B to some other space B prime. This could be some isomorphism between the two, which could be also invertible. If it is one-to-one map, it would be invertible. But here it's itself. So that's why it's called auto. Okay. Yeah, this is a very important point. Actually, yeah, it's a group invariant. The fact that this is group invariant is why it is so useful as a definition of the trend. Okay, now in the notes, there are some examples given. I will not go into the details there, but explicitly, it's done in a very explicit way to write down. We said that this you can think of this as an n by n matrix, So, but in order to see that, you should expand all of this. You should choose a basis, expand all of them in a given basis, right, to see explicitly what matrix you get. And all that has been done in detail here. Okay, so in particular, for example, SU2. So in general, is given some choice of metric. So you can choose a basis. No? So for example, let's say I choose a basis. I will just mention this, but maybe you can take a look at it later at home. So if I choose a basis, say Ti, where it's a basis for V. So if it's n-dimensional, the I must go from 1 to n. So this is the basis. Then I can write x and y both. So x will be some xi ti, and y will be some yi ti, or some numbers x and y. I can always expand it. No? Then this b of xy is simply xi yj b of ti tj. And then, so if I know all of these quantities, there are n of them and n of them, so altogether n square quantities, and not n square because it's symmetric. Since it is symmetric, you only need half n times n plus 1. So those information, once you have that, then you can compute for any x and y. This you can call, let me use the same symbol. This is okay, it's called Bij. This will depend on which Ti and which Tj, which I and j. It will be some number depending on I and j. No? And it is symmetric, so this is the same as Bji. Okay. So this is a metric. So and the inner product between x and y is simply xi yj bij. Metric in this particular basis. So in the notes, this metric, this Bij has been calculated for the basis we have chosen. No? For SU2, we chose the basis sigma I, polymatrices, or sigma I by 2, no? Those bases. And also for SU3, I think SU3 also worked out. Yeah, SU3 is also, oh no, that's left as an exercise. Okay. So you could try to work out, try to go through this, and because now we have lack of time. So if you go through it during this weekend, this remaining part of the chapter, okay, then we can start on Monday. First you ask questions if you have something not clear about that, and then after that we'll move on. This will save some time. Because it's just explicitly working out something. The concepts are all here. It's just explicitly working out for the SU2 case and SU3 case and so on.
So, Professor, the metric we have here, Bij.
Yeah.
Hello?
Yeah.
So the metric we have here, Bij,
yeah.
from the current uniform, this is intrinsic of the algebra we have. It doesn't depend on whichever representation we are using, right?
This representation, that's a good question. But let's say for the kind of algebras we'll be talking about, the rest of the course, which are called simple algebras. I don't want to use this word because I've not defined what is simple algebra. But for simple algebras, it turns out, so instead of this add x, suppose I had used some other representation. That's the question. So suppose I had chosen some arbitrary representation. No? Not just add x, some arbitrary representation. So it will be some r of x, r of y. And I could have taken the trace. Okay, so if I have taken this, will it be the same as that? That's the question, right? Or you go to the basis. So a question in that would be, is this definition B of Ti Tj, the way we have defined it, with using a joint representation, will it be the same as trace Ti, Rti in some other representation, Rtj? Okay. Answer turns out to be that it will be for the class of algebras we are interested in, which will be simple algebras. I have not defined it. We will see it probably next time. What are simple algebras and so on and so forth. But for those classes of algebras, this will be proportional to that. Okay. Some number times this, some overall number, independent of ij. Okay. There are lots of numbers here, right? I mean, as we said, this has half n times n plus 1 numbers here, because it's symmetric, so half n times n plus 1. So all those numbers, so these numbers will be the same as that numbers up to an overall multiplicative factor. Okay. That is actually proven in one of the later chapters. It's proven actually in one of the later chapters. Yeah, that is a good point, yeah. I mean, I'm not finished with this chapter. I have to still discuss a very, very important concept here, that is the last part, the second subsection, 11.2. So let's say just go through the first 11.1. 11.1 in this weekend. So just go through the 11.1 section. 11.1 section. So during the weekend. And see if you understand completely, or if you have any doubts, then we can discuss in the beginning on Monday. Yeah? But 11.2, don't go through that. That's a bit. I'll go through 11.2 on Monday. Okay, because here there are very, very important concepts which will be used again and again in the subsequent lectures. Okay. So. Good. Any questions? Any questions from there? Okay. So, see you on Monday.